Hello, AP Physics 1, it's Mr. Ng with a brief review on kinematics. Today we're going to go through frame of reference, the basic kinematic quantities, you know them, displacement, velocity, acceleration. We'll review what a vector is, what a scalar is, and then the most important part for the AP test, how to interpret those graphs, how to use slope or how to use area under the curve to do some simple math. And then we'll finish up by talking about free fall and terminal velocity. Let's start with the idea of a frame of reference. Not a hard idea. The frame of reference basically says that in order to determine if something is moving or not moving, you have to compare it to something else, preferably something that's not moving. And I have to put that in quotations because think about this situation that John Colley gives us in the book. So we have a person in a train, and that person is walking towards the front of the train. For that person feels as if he or she is moving relatively slowly, because compared to the seat next to him or next to her, it's just a little step at a time, right? The frame of reference is the cabin of the train, or the frame of reference is just the seat, right? But if you were to zoom out, an outside observer observing the train, comparing it to the mountains behind him, that train is going way faster. That means that guy is traveling faster than the train because he's walking along the train, right? The frame of reference matters, right? And there's no such thing as something staying still because you could always find a frame of reference that makes it move, right? So right now you think you're sitting still looking at your phone or the computer, but you're actually spinning because the earth is spinning. And we're also expanding at a ridiculous rate because the universe is expanding, right? Mind blown, mind blown. And then on top of that, we should also review an inertial frame of reference. An inertial frame of reference is for dynamics, for forces, right? The frame of reference is typically something that we talk about when we talk about kinematics, like things are moving. But the inertial frame of reference talks about how much initial inertia do we have. For instance, sometimes we could do dynamics when things are moving at constant velocity. So that has still an inertial frame of reference, right? Don't sweat this part too much. When we get into dynamics, you'll understand what that means a little bit more. Just know that the inertial frame of reference refers to like the initial inertia or the initial forces that are acting on an object, all right, or net forces acting on an object. All right, we're getting into the good stuff. This is the stuff that we remember, our kinematic quantities. Let's start with the simplest one. Where are you? That is the position. Symbol P, a unit, probably meters, right? Sometimes there are coordinates for it, and there's no real formula for it. It's the most basic kind of quantity that you could have. Where are you? The displacement is d, right? And the formula is the change in position, or P final minus P initial. Your final position minus your initial position. Note that it doesn't care how far you walked or how far you traveled. That's distance. Let me explain. Let's suppose that I leave my house and I go north for a mile, then east for a mile, then south for a mile, then west for a mile. My total distance traveled is 4 miles. I'm kind of tired, but my displacement is 0. All right, my displacement is the final and initial position. I'm right back where I started. The displacement is 0, right? And then the unit here is meters. Good. Velocity, the symbol is a V, and the velocity is the change in displacement. All right, so over time. So this is d final minus d initial divided by t final, the final time, minus the t initial. Or I often just do delta d over delta t, right? Delta being the change in displacement over the change in time, okay? And then the unit here is meters over seconds. Pretty darn easy. And if this was a middle school class, it would take a long time to kind of clarify between velocity, which has a direction, and speed. Speed is just the magnitude. It doesn't have a direction. while velocity does, right? We need to do little vector quantities. We'll talk about that. And then finally, acceleration. Acceleration is meters per second squared, or sometimes it's meters per second per second. This is basically the change in velocity, right? It's how much are you speeding up, how much are you slowing down. So I'm driving a car, I'm going 35 miles an hour, and then I see a red light, I slow down, an acceleration occurs, where a negative acceleration where I slow down. I change my velocity. Pretty easy. Formula here is the delta V, change in velocity, over the change in time. Pretty easy. So in the last slide, we talked a little bit about vectors versus scalars. Vectors have a direction. So we're talking about displacement or velocity or acceleration. Scalars only have a magnitude. They only have big or small, sometimes positives and negatives. So these would be things like speed or distance, right? So distance, it's not about the final position, just how far did you freaking travel, and there's no negative distance, but there is a negative speed. Other vectors and scalars that you should remember, force is a vector, but what's not a vector is like energy or temperature, right? Those things only have magnitudes. You don't say I'm 21 degrees Celsius to the north. You're just 21 degrees Celsius. And you can't have negatives, right? It's like, oh, it's negative 20 degrees in Wisconsin, right? But there's no negative 20 degrees south. You know, that doesn't make sense. Okay, good. All right, vectors have a direction, scalars don't. And displacement, velocity, acceleration, they all have a direction. Done. Okay, this is probably the most important slide because it talks about the representations of motion. So let's start with a classic representation that you got to memorize, that of a projectile object, right? Imagine something got shot up and then it fell back down, right? Let's graph that. Actually, let's not even do it in 2 dimensions. Let's just assume that something popped straight up and then went straight back down, right? So here, if this was over time, the x-axis of time, then our object, which starts on the ground, will go up and then fall back down, right? That's the displacement. The displacement versus time graph will look like a little loop, right? Even if it just goes up and down without any lateral displacements. Just because our graph is, our x-axis is time, it's not a position. So at 1 second, at 0 seconds it's on the ground, at 1 second it's up here, and then the next second it's up there, right? Does that make sense, right? So the velocity graph here, if we go this way, the velocity graph will look like this, right? This is something that you memorize, right? Where at 5 it was 0 if velocity is, let's erase that. Okay. Where at 5, there you go. At 5, the velocity was 0, right? And it got more and more negative, right? Let's break that down. Up here, we have a very positive velocity. And down here, we have a positive, but not as positive velocity, meaning initially this thing went up really fast, and then it slowed down until at 5 seconds in, it stopped, right? And then it starts to go down slowly and then fast, right? So here we have a negative velocity that's kind of small magnitude, and then here a negative velocity that's really fast, right? That's projectile motion. Just, you could just memorize it. That could get you through some things, but probably better to just kind of understand that that scenario. And then here, when we get to the acceleration, this whole time the acceleration is going to be 9.8, ladies and gentlemen, because that is the acceleration of gravity. So it does make sense. So as it's going up, it used to go up really fast, but then the acceleration of gravity is slowing it down. So now it slows down, gets to 0, and then the acceleration of gravity makes it go faster and faster. So this bottom part of the graph will go forever, kinda, right? There's friction and things like that. But I don't know. in a ideal system with like some sort of super field that goes forever, it'll just keep going down like that. Okay, makes sense? So let's talk about the relationships here. These are all slopes. To go from the displacement to the velocity, we're talking about slopes. All right, this is talking about the delta d over the delta t, right? So here, if you recall, up here in the very beginning, I have a very sharp slope, which is why I have a big V. And then here I have a tiny slope, like not as sharp, like a more horizontal slope, which is why I have a smaller magnitude V. Slope right here is 0, which is why it's at 0. The slope is still kind of small, right? And then now very sharp slope, right? Which is why it's getting bigger and bigger. Okay? And then here, this slope doesn't change. It's a straight line, which is why it's a horizontal line here, right? Again, it's still the slope going from velocity to acceleration, right? Oops, this is acceleration. This is time, right? So here, the slope is still the delta V over the delta T. And because it's a straight line for velocity, then your slope is, the slope for the acceleration is a horizontal line. Good? Okay. What if we go the other way? If we go the other way, if you were to do the sum under the curve, right? The sum under the curve, if we were to go this way, the area under the curve. It's kind of doing the opposite of the slope. You will find the final velocity, right? That huge velocity at the very end, this big velocity, that's what you found, okay? So here, you could also do little segments of it. So here, if we were to do just the area between like 5 seconds and then 9 seconds, just this area, that will find us the change in velocity between 5 seconds and 10 seconds. It will give us how much faster did it go between 5 and 10 seconds. Does that make sense? Or the other way around, if we found the area under the curve between here and here, notice that they're kind of similar, like in terms of area. So that means at 10 seconds, we should be back at 0 because those two cancel out. And look, the displacement is back at 0, right? To find the total displacement up to 5, we just find the area under the curve between 0 and 5, and that'll give us all the way up to 5, right? It'll give us our final position. So here you can do little segments, right? And when you do the little segments, it just talks about how much did the position change during that time, how much did that velocity change during that time. Again, if you find the area under the curve of an acceleration graph, you're looking at how much did the velocity change during that time. If you're finding the area under the curve of a velocity graph, you're going to find how much did the displacement change during that time, right? So to find the final position, to find the final displacement, you could just do the sum of the entire curve. In this case, it becomes 0. Hope that's not too much, right? So here, let's erase everything. Let's make it a little bit cleaner. Okay, get out of here. Okay, so to go from displacement to velocity, we're doing the slope, the change in. To go from velocity to acceleration, the relationship is going to be a slope, right? The change in velocity. But the other way around, we're going to do the area under the curve, right? To go from acceleration to velocity, area under the curve. To go from velocity to displacement, we're going to do area under the curve. Good. For those of you who are in calc, one way is integration, the other way is a summation, right? Seems pretty good. Last little bit about falling things. Some quick facts. The acceleration of gravity is 9.8 meters per second squared. You already memorized that. In a lot of our problems, we will say 10 meters a second squared because it's faster, right? And it's kind of cognitively better for you, apparently. Sometimes you'll see the word free fall. Free fall means, well, the graph that we just did is in free fall. We ignored friction. But in real life, there's friction. And the faster you fall, the more air friction hits you. So really, when something falls, if something's going to go through free fall, at a certain point, instead of being curved, it goes at a straight line. Like imagine right here, this is a straight line. Okay, because that's a place where, so imagine it's like a baseball that's falling, right? mg, but then at the same time, the force of friction. There's going to be a moment where initially the force of friction is small and mg is still the same, mg, but eventually, as it goes fast enough, these two will become equal. All right, the force of friction and mg will become equal, right? And that's when you reach terminal velocity, and we know that net forces, when they're zero, you're going to travel at a constant acceleration. Good. Hey, I challenge you to maybe draw the velocity or acceleration graph for this. That would be interesting. Okay, in review, a frame of reference is needed. The frame of reference is something that stays still so that you kind of figure out if something is moving. When you go from displacement to velocity, the velocity is the slope of a displacement graph. The acceleration is the slope of a velocity graph. And then the other way around, if I wanted to find the total displacement of a graph and I only have a velocity curve, I'll just find the area under that curve. Hope that helps. Thank you very much for watching.